All right, so now let us try to see where the mean square errors come from, right? So what I'm going to do is to define a kind of a generative process to the problem that we originally had, right? So imagine uh, what we have is that the universe actually has some true underlying line, right? And in a perfect world, what you have is that you will sample some x, which will give you exactly this particular point here, mx plus c, right? So imagine this line is mx plus c. Then all the data points that you get will be in the form of xi, mxi plus c, right? That's in the ideal world. In the ideal world, so all the data points you can see will be like exactly on the line, right? This sample x exactly on the line. But the world is an ideal. So what we're gonna do is to model this non-ideal by perturbating each point by some noise, right? So we're gonna have the same line, the same mx plus c. Oh, sorry, same mx plus c. Okay, again, this is f of x equals to mx plus c. So the way that we are going to do this is to say that, okay, each of the point that we have, we're going to first sample some x, right? So we're going to get some point like here. And then instead of just getting this point and using this point, we are going to fit some Gaussian distribution around this thing, right? This is where the probabilistic things comes in, right? We're going to fix some Gaussian distribution around this thing, and we're going to sample from this Gaussian distribution. So maybe it's sample and an out scale, right? And then again, we're going to sample another x, and then we're going to feed the same Gaussian distribution around this point, right? And then upon sampling, maybe we get a point here. Okay, so what you get at the end of the day is the data might not fit exactly on the line. Okay, so this is the generating process. First, we sample some xi, then we define yi to be mxi plus c, but now we add some noise. We add some noise here. And this noise, I'm going to define this noise as a normal distribution with zero mean and unit variance. Okay? So if we do this definition, this is of course perhaps an unrealistic assumption, but if we make this assumption, we can actually analyze this a little bit more than just here, right? So that is why I quote this thing as realistic. It's not really that realistic either, right? But if we just assume, for instance, that the noise is actually from a Gaussian distribution, then we can do some analysis, right? And let us do the analysis. All right. So with the generative process being defined, we can actually now see where the mean square errors pops up if we apply maximum likelihood estimate to this problem. Okay, so in particular, let us recap a little bit from the previous video. The generative process comes something like that. In this universe, there's some ground truth, some underlying truth that you do not know, just like the coin, you do not know which coin is the true coin that you are holding. So what you do is you use that coin, you flip a few times to sample from that coin, and then collect a bunch of data. And using those data, you try to infer which coin the data comes from, right? And you do that using maximum likelihood estimate. So it's the same thing for this coin. You do not know what the M and C is. So what you do is you just sample a bunch of data using this M and C, and then using this data, try to infer what the true value of M and C is, using, again, maximum likelihood estimate, right? So recall the data generating process goes something like that. For each of the data y superscript I, you generate from x mx superscript I plus c, but you get perturbated by a little bit of noise, epsilon, where each of this epsilon is normally distributed with mean 0 and variance 1. Okay, and if you think about this, this epsilon is essentially just a random variable, right? Recall what a random variable is. Then this, if we assume this is constant, then this y superscript I is essentially just a random variable with a very simple form, right? This is going to be a random variable of the form normal distribution with mean mx superscript I plus c and variance 1. Okay? So let us try to analyze just one data point, right? Assume that we see, assume we observe, assume that we observe x superscript I and y superscript I. Okay, so what we really want to ask is, what is the probability that we see y superscript I if we know what the x superscript I is and we fix some m and c, right? So it's the same thing as the coin example. If we assume that our coin is, C0.2 or C0.5, what is the probability that we see the data? Okay, so we are doing the same thing here. But here's the thing, right? This probability of y given x mc, well, that's essentially what this equation is about, right? We know m, we know x superscript I, we know c. So y superscript I just have a very simple distribution. It's essentially just the PDF of a Gaussian distribution with mean m x superscript I plus c and variance 1, right? So we can just write it down. This is 1 over square root of 2 pi e to the power of negative y superscript I minus the mean of this distribution, which is mx superscript I plus c square over 2 times the variance, which is 1, right? So this is essentially the probability that we see a particular data point. So if we were to see multiple data points, then we can just use the product rule of probability to just product them together, right? So if we assume that we observe a set of data, x superscript 1, y superscript 1, up to x superscript 5, y superscript 5, right? Let's say we only have 5 data points. Then the probability that we see this data, D, given M and C, is essentially just the product over all the points of this PDF here, e to the power of negative y superscript I minus m x superscript I plus c square over 2. Okay, so here's the trick, right? What we really want to do is to maximize this quantity here, right? This is the this is the likelihood that we see the data given we assume some hypothesis, given we assume what M and C are. So we want to maximize this quantity. So it turns out that if you want to maximize this quantity, and you want to know what M and C maximizes this quantity, you can essentially just try to look at what maximizes the log of this quantity instead, right? Because log is a monotonically increasing function. So let's see what happens if we log this thing, right? If we log this likelihood function here, what you have is essentially the log of a product, which is the sum of logs, right? Which is the sum of logs. So let us do it. You get the sum of the log. Constants doesn't really matter in optimization, so I'm going to just drop it. Just know that there is a 1 over square root of 2 pi terms here. I'm going to drop it, but we have log of the exponential of the whole thing here, right? Square over 2. And then what we have, right? Log and exponential cancel out each other, right? So what we essentially get is summation of I equals to 1 to 5 of, what do we have? 1 over 2, or negative 1 over 2 of y equals to I minus m x equals to I plus c squared, right? So again, if you want to maximize this log likelihood, it really doesn't matter what this half is, right? So this half essentially is useless. We can ignore it. And if we ignore it, what we essentially now have is just negative of the mean square error, right? So recall that what we want to do is to maximize the likelihood, and our likelihood is the negative of the mean square error. So it means that what we want to do is to minimize the mean square error. And we're done, right? We essentially derive the mean square error in a more principled approach, using just some probabilistic assumption about what the noise is. Okay. Again, if you can't follow this thing, try to recall back to your 2334 or the 2132 knowledge, and try to see if you can follow this through. But if you can't, really, it really doesn't matter, because this is really outside the curriculum of 3244. Okay. But I hope like this gives you context, right? This gives you why certain assumptions are made. They are not really made arbitrarily. At the very least, for classical machine learning methods, they're not really that arbitrary. I can't say the same for deep learning approaches. You'll see a lot of ad hoc hacks around in the later few weeks, but at the very least, for the first few weeks, things are actually pretty principled, right? They have grounds in probability theory and statistics, and I really hope that this is actually helpful, right? So this concludes the end of our first session of Quick Take to Machine Learning. Let's see what we'll have next week. I hope you enjoy the course coming ahead. So goodbye.